So we continue with the next topic of module 4, that is the syllabus. Copolymers, definition, types of copolymers, namely random, alternating, block and graft. These are the classification of copolymers. ABS copolymer, that is a special type of copolymer which has wide applications. Conducting polymers and doping. So conducting polymers, these are polymers which can conduct electricity, and doping, the process by which the conduction or the conductivity of such polymers can be improved. Polyaniline and polypyrrole, two important examples of conducting polymers. OLED, principle, construction and advantages. OLED stands for organic light emitting diodes. So polymer is defined like this. It's a long chain molecule formed by joining of large number of monomers via chemical bonds. So long chain molecule formed by joining of large number of monomers via chemical bonds. And monomer, these are small molecules which combine with each other to form the polymer. So these are two important definitions, polymer and monomer. The chemical reaction which leads to the formation of a polymer, that is called polymerization. And the number of monomer units in a polymer, that is called degree of polymerization. So these are four important definitions which you should always remember when you are discussing polymers. Classification of polymers. Polymers can be classified on the basis of different properties. So the first important classification of polymer is based on the polymerization reaction. So on the basis of the reaction, we can classify a polymer into two categories. One is known as addition polymer and the other one is called condensation polymer. Now we can see what is the difference between addition and condensation polymer. An addition polymer, the reaction, the polymerization reaction taking place is addition. Two monomers, they just add up to give, or not two, more than one monomers, they add up to give a polymer. Okay, the monomers will be having olefinic bonds. That is one peculiarity here. The monomers which are involved in addition polymerization, they have olefinic bonds, that is double bonds, and the polymer propagates through these bonds. The polymers are formed due to the rearrangement of these olefinic bonds. Let us look at an example. This is ethylene. Ethylene polymerizes to give polyethylene. So you can see here this double bond, it breaks and the polymer extends from these two portions. Okay, the polymer propagates. Propagating of a polymer means the formation of the long chain. So that takes place due to the breakage of this double bond. Similarly, another example, 1,3-butadiene. It's a compound containing two double bonds, diene, that polymerizes to give polybutadiene. So you can see here these double bonds rearrange and the polymer is formed through these two carbon atoms, these two ends. Okay, this double bond rearranges to the middle and the polymer forms from these two ends. So polymer propagates through these double bonds. Now in these two examples there is a small difference. Here, if in the case of ethylene, if you are numbering the carbon atoms, these are carbon atoms 1 and 2. The polymer is formed due to the combination of carbon atoms 1 and 2 of ethylene. So this is known as 1,2 addition. Whereas in case of butadiene, the carbon atoms are numbered as 1 and 4 and the polymer is formed due to the combination of carbon atoms 1 and 4 of butadiene, and so this is called 1,4 addition. So there are two types of addition polymerizations, 1,2 additions and 1,4 additions. Condensation polymerization. So here the reaction, the name itself suggests that the reaction is condensation. Condensation means combination of two molecules by the removal of a small molecule. The monomers have more than one functional groups. That is one important characteristic here. The monomers have more than one functional group, and the polymer propagates by elimination of small molecules. So two monomers combine together by the elimination of a small molecule. That reaction is called condensation. For example, this is a dicarboxylic acid and a diamine. They combine together. You can see here dicarboxylic acid, diamine. They combine together by removal of one molecule of water and they form this polymer. Okay, so this is an amide. This is a polyamide. This CONH, that is a amide group, and this polymer is called a polyamide. So this is an example for condensation polymerization. So these are the two classifications of polymerization on the basis of the reaction. On the basis of the number of monomers, we can classify a polymer into again two categories. If there is only one monomer or one type of monomer, that is called homopolymer. Okay, only one type of monomer, like for example polyethylene, that contains only one monomer, so that is called homopolymer. If there are more than one type of monomers, then that is called as a copolymer. So we will be discussing about some examples of copolymers. Now before that, copolymers, they can be classified in different ways. Copolymers can be classified into four different categories, and these are called as alternating, block, graft and random copolymers. Alternating, block, graft and random copolymers. Now what are these? What are these or how they can be classified like this? Suppose you assume two monomers A and B. They are combining to give a copolymer. Then alternating copolymer means each of this monomer A and B is alternating. Now you can look at the structure. We have A, B, A, B, A, B structure. So this is called alternating copolymer. Block copolymer, it means that you have one block of A and one block of B, something like this. A forms a long chain polymer, a block, and B forms another block, and these two blocks get combined together. This is called as a block copolymer. Random copolymer means the monomers A and B combine in a random fashion. There is no particular arrangement. A, B, A, B, 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 A, B. There is no particular arrangement. Random arrangement. And the fourth category, that is called graft copolymer. Graft copolymer means it is something like this. You have a long chain of A and you have several short chains of B which are grafted to this A at different positions. Okay, that is called a graft copolymer. So this is the classification of copolymers. Now here you have a very important KTU question. Write the different types of copolymers formed by the monomers A and B. This question is a very important question from your KTU examination viewpoint. Let us go to ABS copolymer. This is a very important example of a copolymer. ABS copolymer. ABS stands for acrylonitrile butadiene and styrene. These are the three monomers which combine to give this polymer. Acrylonitrile, butadiene and styrene. So ABS copolymer. What is ABS copolymer? ABS copolymer is a copolymer formed by the addition polymerization of acrylonitrile and styrene in the presence of butadiene. Okay, that is very important. Acrylonitrile and styrene, they polymerize in the presence of butadiene, and that gives ABS copolymer. Let us look at the reaction. The reaction for synthesis. This is acrylonitrile and this is polybutadiene and this is styrene. So acrylonitrile and styrene are polymerizing in the presence of polybutadiene and you get this product. This is ABS, acrylonitrile butadiene styrene. What are the properties of this compound? Acrylonitrile butadiene styrene. High impact resistance. That is a very important property which gives a lot of applications. We will look at these applications. Good chemical resistance. It is chemically resistant. Then excellent abrasion resistance. High resilience. Resilience means these are elastic materials. So the percentage of elasticity, that is expressed as resilience, and improved strength. So these are the important properties of ABS copolymer. Now these properties give ABS some special applications. What are these applications? Protective headgears and car bumper. So in a car, the bumper is the portion which is most vulnerable to impacts, isn't it? Impacts or abrasion that happens mostly on the bumper. The car bumper is made of ABS polymer. Golf club heads, they require a lot of strength, so you need ABS copolymer. Kitchen appliances, then computer parts like for example the keyboard caps, they are made of ABS copolymer because you are constantly pressing on them. Okay, a lot of impact, a lot of abrasion happens on them, so you require a very strong material like ABS. So these are some of the applications, these are some of the important properties of ABS. From the examination viewpoint, what is ABS? What are its important properties and applications? This is a frequently asked question. What is ABS? So ABS is a copolymer of acrylonitrile, butadiene and styrene. Then important properties and important applications. Kevlar. Kevlar is yet another important polymer. You might have heard the name Kevlar. It is a trade name and Kevlar is used as bulletproof vest. So it's a very important engineering material. Kevlar is also known as aramid fiber. Aramid is a short form for aromatic polyamide. Aromatic polyamide, the AR of aromatic and the AMID of polyamide, they combine to give aramid. So aramid fiber, it's a fiber type material and so you can spin it into fabrics. Amide, polyamide or amide group means it is NHCO, C double bond O. Okay, NHC double bond O group, that is called amide. And polyamide is a polymer containing amide linkage. We have seen earlier the example of condensation polymer, and that it's a polyamide. If the polymer is, or if the monomer is aromatic, if the monomer forming the polyamide is aromatic, then that is called aromatic polyamide. Aromatic polymer containing amide linkages. And Kevlar is an aromatic polyamide. The actual name of Kevlar is a trade name. The actual name of Kevlar is polyparaphenylene terephthalamide. Okay, it's a little bit long name, polyparaphenylene terephthalamide. Now let us look at the synthesis of Kevlar. Okay, synthesis. You will get a little more idea about the name when you look at the synthesis. So Kevlar is synthesized from these two starting compounds, phenylene diamine and terephthalonyl chloride. Okay, phenylene, 1,4-phenylene diamine. Look at the structure here. It's a benzene ring and 1 and 4 positions. You have amino groups, that is 1,4-phenylene diamine. Terephthalonyl chloride, again a benzene ring, and at the 1 and 4 positions you have carbonyl chloride. This is carbonyl chloride, C double bond O Cl, carbonyl chloride. Okay, that is called terephthalonyl chloride. So 1,4-phenyldiamine and terephthalonyl chloride, they are condensed. Condensation, polymerization by the removal of hydrogen chloride or hydrochloric acid, and you get Kevlar. This is the structure of Kevlar. Polyparaphenylene terephthalamide, Kevlar. The structure, this is the structure of Kevlar. Now structure of Kevlar is a little bit important because if you look here, the Kevlar consists of different sheets. Okay, different sheets. This is one sheet, this is another sheet, this is the third sheet. These are stacked one over the other. And there is another thing, the thing that is shown in the red color here, that is the oxygen of the carbonyl group in one sheet is connected to the hydrogen of the amino group in the other sheet by a hydrogen bonding. So there is hydrogen bonding between the different sheets. So this hydrogen bonding is responsible for the high strength of this material. This material is a very strong material. That is why it is used in bulletproof vests. Okay, so this strength is derived from this hydrogen bonding. So there is hydrogen bonding in between the different sheets of Kevlar. Okay, the properties: high tensile strength, 3.6 gigapascal, that is a tensile strength, very high strength material. It has high relative density and it maintains its strength and resilience down to cryogenic temperatures. Cryogenic temperature means the temperature of liquid nitrogen, which is approximately minus 160 degrees centigrade. So even at such low temperatures, Kevlar maintains its strength. It has low thermal conductivity and it can be spun into ropes or fabric sheets. So that is a very important property, and due to that it is finding application as bulletproof vests. So these are the important properties of Kevlar. Applications. The most important application: protective materials like bulletproof vests. Then fiber optics. Now in optical fiber cables, the insulation, the cable insulation is made of Kevlar because you need a strong material. The cables are mostly underground, and if by accident somebody digs into this cable, then it should be protected. So the protective covering is given of Kevlar. Used in the field of cryogenics, since it retains its strength at very low temperatures, it can be used in the field of cryogenics, and it is also used as a thermal block to minimize heat leaks. Okay, as a thermal insulator we can use this material, and it has acoustic applications also. That is, a cone of a loudspeaker is made of Kevlar. Okay, that gives better sound performance. So these are some of the applications of Kevlar. Kevlar again is another important topic as far as your syllabus is concerned. This is a frequent question in Kevlar. What is Kevlar? Explain the preparation and exceptional properties of Kevlar based on its structure. So that is a very important. The preparation, properties and the structure of Kevlar, that is very important. So this is about copolymers. The two important copolymers we have seen. One is ABS copolymer, that is an adhesion copolymer, and this is Kevlar, that is a condensation copolymer. So two types of copolymers: adhesion copolymer and condensation copolymer we have seen. Now another important question, KTU question, is what are copolymers? Illustrate with adhesion copolymer and condensation copolymer. So that is what we have seen here. Adhesion copolymer, example ABS, and condensation copolymer, example Kevlar. On to yet another important polymeric material called conducting polymers. Normally polymers are insulating. For example, the common polymers that we use: polyethylene, polyvinyl chloride, PVC, Teflon, all these are insulating materials. But we can convert a polymer into a conducting material. So such polymers, they are called conducting polymers. Definition for conducting polymer is like this: organic polymers that conduct electricity due to the presence of delocalized pi electrons. That is one thing that is very important. Organic polymers that conduct electricity due to the presence of delocalized pi electrons. That is called as a conducting polymer. And the conductivity of these polymers, they are comparable to metals or semiconductors. So there are polymers which show conductivity equal to silver. Silver is a highly conducting metal. So we can synthesize polymers which show a conductivity nearly equal to silver. Okay, and normally the conductivity is in the range of semiconductors. How are conducting polymers classified? That is one very important thing. How can we classify a conducting polymer? Generally, a conducting polymer is classified into two categories. One is called intrinsically conducting and the other is called extrinsically conducting, similar to semiconductors. Okay, but there are some differences. Only the name is similar, the features are different. So intrinsically conducting and extrinsically conducting. Intrinsically conducting means what? Intrinsically conducting means the conducting property is inbuilt, whereas extrinsically conducting means the conducting property has to be introduced. As such, it is not conducting. We have to do something and introduce conductivity. Intrinsically conducting means as such, when the polymer is formed itself, it shows conductivity. Intrinsically conducting can be further classified into two categories. These two categories, what are these two categories? One is called undoped polymer and the other is called doped polymer. Okay, there are some similarities between the classification of conducting polymers and the classification of semiconductors, but there are differences also, so you should not get confused. So please listen carefully. Undoped polymers and doped polymers. What do you mean by undoped and what do you mean by doped? We have to see this in detail because intrinsically conducting polymers are the most important type of polymeric materials, polymeric conducting materials. Okay, let us go to undoped polymers. What do you mean by an undoped polymer? Undoped polymers, they contain alternate single and double bonds. Okay, alternate single and double bonds, and the electrons can be easily delocalized. When they contain alternate single and double bonds, the double bonds can rearrange, and so the pi electrons, they can be easily delocalized, and that leads to conduction. So you don't have to do anything. As such, they are conducting. The undoped polymers, they are conducting as such. The mechanism of conduction is transition of electrons between HOMO and LUMO. HOMO stands for highest occupied molecular orbital. LUMO stands for lowest unoccupied molecular orbitals. So there are several molecular orbitals which are formed when the polymer is synthesized, and out of the highest molecular orbital which is occupied, which contains electrons, that is called HOMO. It can be comparable to the valence band in semiconductors, and the lowest unoccupied molecular orbital, the just orbital above this HOMO, that is called LUMO, that is comparable to the conduction band, and so an electron can undergo a transition between HOMO and LUMO, similar to valence band and conduction band transition. Similar to, not exactly, but similar to valence band and conduction band transition in semiconductors. So this is how undoped polymers undergo or show conductivity. What are doped polymers? Now, doped means the process of doping. Conductivity of polymers can be enhanced by doping. Suppose you have a conducting polymer, you can change its conductivity by doping. Doping means transforming the polymer into charged ions. That is doping. The process of transforming a polymer into a conducting polymer into charged ions is called doping. And these charged ions, they are called polarons or bipolarons. Now why two names, polaron or bipolaron? If there is only one charge, that is called polaron. If there are two charges, that is called bipolaron. Okay, so mostly the conducting polymer, after doping, it will have a single charge, then that is called polaron. If it has two charges, that is called, by just like monovalent and divalent ions, we call them as polarons and bipolarons. Doping can be done by two methods, similar to semiconductors. Now you know in semiconductors there are two ways of doping. Similarly here also there are two ways of doping. One is called p-doping and the other is called n-doping. Now the method of doping is different. It is not like in semiconductors. So but doping can be done in two ways, p-doping and n-doping. What is the mechanism of conduction in these polymers, in doped polymers? The mechanism of conduction is a movement of polarons or bipolar. These charged ions, they will move, or the charge will move in the polymer, and that leads to conduction. So movement of polarons or bipolarons causes conduction. Let us see about doping, p-doping and n-doping, how it is done. Let us compare these two types of doping, P and N. In this table you can see p-doping is done via oxidation, whereas n-doping is done via reduction. Okay. Oxidation can be done using Lewis acids. Example, aluminum chloride. Aluminum chloride is a Lewis acid. Whereas reduction can be done by using Lewis bases. Example, lithium. P-doping creates positive polarons and N-doping creates negative polarons. That is one important point. In p-doping, the charge is a positive charge, and in n-doping, the charge created is a negative charge. So these are some points of comparison between p-doping and n-doping. So that is about intrinsically conducting polymers, two types, doped and undoped. Coming on to extrinsically conducting, they can also be classified into two categories. One is called polymers with conducting fillers and the other is called polymers with conducting blend. Now if you take an insulating polymer and you put a filler which is conducting in nature, then the whole material will become conducting. That is called polymers with conducting fillers. Generally metals are added as fillers. So these polymers are called metallopolymers, metallic fillers. Okay, so if such polymers are called metallopolymers. Or in other cases, what we can do is we can blend, we can combine a conducting polymer and an insulating polymer. Like for example, polystyrene is an insulating polymer, but polyacetylene, that is a conducting polymer. These two can be blended together. You will get a very good material. You can combine the properties of both these materials. Polystyrene is very strong. Polyacetylene is highly conducting. So if you blend them, you will get both the properties. You will get the strength of one material, you will get the conductivity of other materials. So such blends, they are called polymers with conducting blends. So these are the two types of extrinsically conducting polymers, polymers with conducting fillers and polymers with conducting blend. KTU question, explain the classification of conducting polymers. Okay, now this question can be asked for several marks. It's a 4-mark question. It can also be asked as an 8-mark question. So depending on the marks, the details should be included. Okay, you have to go in more depth if it is asked as an 8-mark question. If it is asked as a 4-mark, you just have to give the basic classification. General properties of conducting polymers. Highly conducting like metals, can be doped with acids and bases. That is one very important property because the conductivity can be changed by doping. Oxidized and reduced forms show different colors. That is also very important because this can be used as sensors. You can use such materials as sensors because under one and condition, like in oxidized condition they will show one color, in the reduced condition they will show another color. So it is very suitable for use as sensors. Exhibits magnetism. So these are some of the general properties of conducting polymers. General applications: electrodes for batteries, supercapacitors, sensors and biosensors. That is an area where a lot of application is developing for conducting polymers. Then organic solar cells, yet another important area. And finally display panels or OLED. We will be discussing about OLEDs in detail later. So these are some of the general applications of conducting polymers. Now there are two varieties of conducting polymers, and that we have to discuss the synthesis of these two in detail. Polyaniline. Polyaniline is also called as pani, not pani, it should be pani. So polyaniline or pani. And what is polyaniline? Polyaniline is a conducting polymer of aniline, and it is the first conducting polymer which was discovered. Maybe about 150 years back, polyaniline was discovered. How can we synthesize polyaniline? There are two methods for synthesis of polyaniline. One is called the chemical and other is called electrochemical. This is a chemical method. In the chemical method, you are adding an oxidizing agent like ammonium persulfate or ferric chloride. You are adding some chemicals. That is why it is called chemical method. So aniline is the monomer. Aniline is polymerized to give polyaniline by using some chemicals like ammonium persulfate or ferric chloride. The reaction taking place is oxidation. Aniline oxidizes to polyaniline. So this is the chemical method. Another method, instead of adding chemicals, you do the same process by passing electricity. That is called the electrochemical method. Electrochemical method. Aniline, when you pass electricity, it polymerizes and it gives polyaniline. Now in the chemical method, the polyaniline that is formed is in the reduced stage, whereas in the electrochemical method the polyaniline formed is in the oxidized stage, and the oxidized state of polyaniline is conducting in nature. Okay, the oxidized form of polyaniline is conducting. So this is how polyaniline can be synthesized. So one important KTU question: explain the chemical synthesis of polyaniline. Write 3 applications of polyaniline. The applications, they are general. The polyaniline can be used for any of the above mentioned or earlier mentioned applications. Explain the chemical synthesis of polyaniline. Write 3 applications of polyaniline. The next important conducting polymer, that is polypyrrole, represented as PPY. Polypyrrole is a conducting polymer of pyrrole. Let us see the synthesis. How we can say? Here again there are 2 methods. One is the chemical method. So this is the chemical method, pyrrole. This is pyrrole. This is pyrrole. Pyrrole oxidized to polypyrrole using some oxidizing agents, ammonium persulfate, ferric or ferric chloride. Same thing can be done by passing electricity. That is the electrochemical method. Pyrrole converts to polypyrrole by passing electricity. So the chemical method again gives the reduced form, and the electrochemical method gives the oxidized form. The oxidized form is conducting, and the oxidized form consists of bipolaron. Okay, the oxidized form consists of bipolaron. So the conduction is due to movement of bipolar. So this is a very important thing in polypyrrole. The oxidized form is conducting and the oxidized form consists of bipolar ions and its movement causes conduction. So this is the synthesis of polypyrrole. Since pyrrole is basic, it can be doped using acids only. That is, only P doping is possible in case of polypyrrole. So that is an important KTU question. Which kind of doping is possible in polypyrrole and why? So only P doping is possible because pyrrole is basic. So you can use only acids for doping. If the material is neutral, we can dope it with acids or bases. But if it is basic, we can dope it using acids only. So this is another important university question. So that is about polypyrrole. Moving on to organic light emitting diodes or OLED. We have mentioned that earlier as an application of conducting polymers. Conducting polymers are used in OLEDs. So what is an OLED? LED, light emitting diode, we may be aware of that. These are diodes. When you pass the current, it will emit light. An organic light emitting diode means organic compounds are used as the semiconducting layers. So in a diode, you have a p type and an n type semiconductor, and this semiconductor material, if you are using an organic compound, that is called as OLED. For example, these are two common compounds, AlQ3. Q stands for quinacridine. So AlQ3, that is a compound which is used as OLED, which is used in OLED, or you can use a polymer, polyfluorine. Polyfluorine. This is a polymer which is very commonly used as OLEDs. So these are two examples. Now, how can you construct an OLED panel? The OLED panel, it is similar to the LED panel. Okay, both are same. The only difference is in the material. The material will be different. So here you see you have a cathode and you have the electron transporting layer, that is a n-type semiconductor, and you have the hole transporting layer, that is a p-type semiconductor, and then you have a transparent anode, and you have the substrate, that is mainly glass. So this is how the construction is done. So this is a p-type semiconductor, this is an n-type semiconductor. When you combine, you get a p-n junction. When the p-n junction is formed, some recombination of electrons and holes will take place. Some electrons from here will move here, holes will move there. A small recombination takes place and it comes to an equilibrium. Now in this situation, suppose you are applying a voltage, then what happens? These electrons and holes, they will come back to their actual positions, and that excess energy, that is released in the form of a radiation of light. This is a very simple description. Okay, it's only a very simple description. We are not going into the details, into the physics of that. In very simple terms, we can describe it like that. When the voltage is applied, recombination of electrons and holes or redistribution of electrons and holes takes place. That excess energy, that is released in the form of a radiation, and that comes out. So this is how an organic light emitting diode works, exactly like an LED. The only difference is the p-type and the n-type semiconductors, these two layers, they are formed using organic materials. So this is how an organic light emitting diode works. Now what is the advantage of an organic light? Why do you want OLEDs? What is the problem with the LEDs? You can do anything with LEDs also using inorganic semiconductors. Why do you want OLED? So the advantages: thinner and lighter. That OLED panels can be made thinner and lighter. You can have a screen or you can have a television of the thickness of a paper. That is what it is said. Some company, I think it is LG, they have made a panel which is as thin as a paper. Then more efficient and flexible. These are flexible panels. no backlight is necessary. For LCD panels, you will require a backlight, but here you don't require a backlight. Less power consumption compared to even LED, the power consumption is less. Better viewing experience. The viewing angle is very much different. You can even view at nearly 180-degree angle. Less response time. Response time means when you switch on the display, there is a small gap from the time of switching on and the time of appearance of the display. That is known as the response time. So response time is very less compared to other displays. So these are some of the advantages of OLED panel. So in OLED, one frequently asked question: brief out the basic principle, construction and working of OLED. Principle, construction and working, or even advantages, they are also frequently asked. So this is how an OLED works. So this is all about conducting polymers. The conducting polymers, the classification, the properties, applications, then two examples, polyaniline and polypyrrole, and finally OLED, the principle, the construction, working and advantages. So this is all about conducting. So this is all that you have in this topic of the fourth module, polymer chemistry.